Hello, everyone. We will now hear from Professor Li Weiping of Hong Kong University of Science and Technology, who will give us a talk on high Gromov-Witten invariants of Calabi-Yau threefolds.
Okay, so I would like to thank organizers for the invitation. So I will talk about the higher genus Gromov-Witten invariants of Calabi-Yau threefolds. So this is joint work with Huai-Liang, Guo Shuai, Jun Li, Melissa Liu, Zhou Yang at different stages. Okay, it's not the single work of the joint work. Okay, so I will divide into two parts. First, one part, in fact, part one, I give several talks, several places before. Some of you probably heard about it. So it's a review of an effective method called mixed spin P field theory, MSP for short, to study higher genus Gromov-Witten invariants of quintic Calabi-Yau threefolds. So it's a hypersurface in P4. So in the talk, I will concentrate more on the geometric construction and less, in fact, none on the computation part. But in fact, the computation part is the crucial part of this whole project. Yeah. But I will not talk about it because it's very complicated, and also I'm not expert. Okay, but Guo Shuai probably will give a better talk on this part. Part two, I will talk about recent work, which is generalization of this method to Calabi-Yau, a complete intersection of toric varieties. I will point out why this is not a general generalization, and what kind of difficulties we encounter, and how we overcome these difficulties. Okay, so quintic Calabi-Yau threefold was very simple, given by this W5, degree 5 of phi variable. The quintic Calabi-Yau threefold will be the locus of this polynomial in P4. And of course, we are interested in counting the number of curves of given genus, of given degree, denoted by genus G, D, N for the number. So I review a little bit because I'm assuming that not everybody here in the audience know Gromov-Witten. Some are top experts, some are not. Okay, but anyhow, so we knew that this famous work by Candelas and his collaborators in 1991 used mirror symmetry to get a closed formula for genus 0. So here, genus 0. So N0D, 0 for the genus of the quintic Q. But the method is physical, which means it's not mathematical. The method is to find another Calabi-Yau threefold called Q hat, called mirror, and then study the moduli problem of complex structures on this Q hat, different manifold, and then compute something else, compute something called the periodic integrals, and somehow, due to physical conjectures, they claim that the formula gives you the N0D on the quintic, on the Q. Okay, so how to do this mathematically, which means directly count the number of curves on Q instead of Q hat. Okay, so, but mathematically, it's easier to count maps instead of counting curve. Okay, so therefore, this due to Kontsevich, instead of consider space of curves on Q, we consider space of stable maps. So this is the modular space of stable maps from the curve C to the Q, with the requirement that the degree of this curve is D inside here. Lower two, sorry, okay? So C is required to be a nodal curve, okay? Cannot be too complicated, it's just a nodal curve with a mild singularity, nodal singularity. And the map will have a requirement that has a finite automorphism. So that's finite automorphism means stable here. Because this stable terminology is very important in my talk, so I will emphasize here. Okay, the modular space, this modular space is compact, but if the modular space were set of points, then you just count how many points inside the modular space, okay? So the counting curve, you just count the number of points here. But the problem is, the modular space, by deformation theory, we knew is dimension 0. However, the actual dimension of the moduli space is bigger than 0. So therefore, you cannot just naively count number of points because this space is higher dimensional. So therefore, we have to count in a smart way, and this smart way somehow found by Jun Li and Tiangang and Baron and Fantecchi. They show that the modular space, in fact, has a virtual class, virtual fundamental class. So I have a virtual here. So virtual fundamental class. This virtual fundamental class has a dimension 0 inside the total modular space. Therefore, this is a mathematical definition of so-called Gromov-Witten invariants. NGD will be the degree of this virtual cycle, which is dimension 0. But because there's automorphism involved, so in fact, it's not integer, it's a cube. Okay, so that's why this is Gromov-Witten invariance. Okay, so how do we compute genus 0? Okay, so conjectured by physicists. Oh, sometimes it's just computed by physicists using physical methods. And this computation is many years ago already, so carried out by Huai-Liang, Liang, Liu, Yau. And this is referred to as A model or A side computation. Okay, on Q instead of Q hat. So what's the method? The method is the quintic is in P4. So there's a torus action on P4. And then we use that torus action somehow to compute. Okay, so one way that can be done is first, the dimension is wrong is due to abstraction sheaf. Okay, so therefore the virtual cycle in this case is just the top chunk class or Euler class of this abstraction sheaf. And this abstraction sheaf in this case is a vector bundle. That's the first thing that's make us we can work. Second, the modular space of stable maps to P4 is kind of smooth. Smooth means static sense. Okay. So it's smooth somehow, and then because it's smooth, it's a vector bundle. To calculate the Euler numbers, you can use Artia-Bott formula, but making use of torus action. Okay, so in terms of computational, first step seems to be very simple, but to do it, to package it in a way is super complicated. Okay, the combinatorial methods developed here by Gimental and by these people, in fact, are fundamentally important. Okay, because there's many things introduced in the whole business. Okay, will be used later. Okay, so now I emphasize that for genus 0, the computation is just computation of a top 10 class of a bundle. But from here to here, in fact, it's very complicated. Okay. Okay. However, if I want to go to higher genus, then there's a huge difficulty. The first difficulty is smoothness fails for positive genus. And also, it will not be a virtual class. The virtual cycle, in fact, again, will not be an Euler class of any bundle. So which means the abstraction sheaf will be honest sheaf, not the bundles anymore. So there are these two difficulties pose huge difficulties. Physicists, this Chikoti is here, I think. It's not in this room, but it works here. Yeah. Oguri and Vafa in 1993 formulated very famous structural results on higher genus Gromov-Witten invariants of the quintic. So I will not emphasize on this because it's more computational, but it leads to many important results. Some of the results, in fact, are closed formulas. Among these results, for example, Yamaguchi-Yau finite generation conjecture, which I will not mention. For example, genus 1 Gromov-Witten invariants of quintic, that's explicit formula. And finally, the BCOV conjecture on finite root, some root. The BCOV conjecture says that somehow the higher genus Gromov-Witten invariants can be written as Riemann sum, Feynman sum, and then there is 3G minus 3 ambiguity. So that's BCOV, which means up to 3G minus 3 ambiguity, we knew the higher genus Gromov-Witten invariants for quintic, any genus. Okay, and also there this work that we are now going to cover that really determine the formula up to genus before it's 51, now at maybe 71, or maybe what's the current 101. Okay, yes. Okay, okay. So very complicated methods. Okay, very sophisticated. Okay, maybe let me mention a little bit of what's the difficulty in genus 1 case. The genus 1 case, there's a problem coming from the ghost component. Okay, the ghost component means the map that contract the genus 1 curve into a point. And the degree D will be carried on the rational tails or bridge, whatever. Okay, so over there, the degree is there. But this genus 1 main component, in fact, go to 0, map to 0. So this is called the ghost component. And this ghost component will cause the dimension jump. Okay, so the modular space has many components, and this ghost component dimension is higher than the other components. And then, therefore, the modular space is not smooth anymore, and the virtual cycle is not the Chang class of a vector bundle, so this method definitely cannot work. So how do you do this? So this was studied by a group of people long time ago. So success for genus 1 Gromov-Witten invariants, in fact, comes from the detailed study of this ghost component by Jun Li and Zinger, Zinger, and Zinger himself for many series of papers. And what's the technique there is use blow-ups, because you have singularities, you do the blow-up, and then you need to introduce something called reduced invariance. So Zinger computed in reduced invariance. Okay. So there's another method to calculate genus 1 is by Fontaine, Bonsic, and Low use quasi-maps and work process to reprove Zinger's formula. So Zinger's formula is a formula conjectured by BCOV. So that formula is explicit. So that can be computed. And you can see here, I want to emphasize that when genus go higher, the work on geometry is much more. So which means we have to spend more time on the modular space. Okay, so for genus 0, basically you don't need to spend much time. Okay, sorry. You don't need to spend much time because of you just calculate Chang class. Okay, it's very simple geometry. Okay, but genus 1, you have to do blow-ups, and you have to introduce reduced invariance. And calculation of reduced invariance somehow is done by Zinger. The calculation is not super complicated. Okay, but combinatorics is fine, but geometry is more complicated. So you can imagine that if we go higher genus, and in fact there's a try to do genus 2, use the same method, and then the components will have more, and blow-up is some kind of out of control. Okay. So for example, for higher genus, I can talk about this famous work. It's not Calabi-Yau, but still very famous. So Gimental and Telemann developed a method for higher genus Gromov-Witten invariants in a semi-simple case, for example, PN or other case, but this is not Calabi-Yau case. And a long time ago, Malik and Panda already studied inductive method for higher genus Gromov-Witten invariants. Fan Honglu and Weiping Li, they found a method. This is quite not long time ago, but relating any genus Gromov-Witten invariants of hypersurfaces with the ambient spaces. Chen Qile, Guo Shuai, Yang Zhou, and Ran, they also developed a method using log geometry to study higher genus Gromov-Witten invariants of Calabi-Yau quintic. So you can see over here, the focus, in fact, is all on the geometry. Okay. So you have to spend a lot of time on geometry. So this method uses degeneration. So degeneration, of course, is a geometry. Okay. So this is a geometry. This is also geometry. Okay. But the question is, you have a good geometry set up, but whether you can have effective computational method. So you have a method here, but can that be effective? Okay. All right. So now I will talk about the effective method. Okay. So this method is somehow coming from I don't know, out of blue, but Yongbin Ran asked me to study this so-called Gromov-Witten FJRW correspondence, Calabi-Yau Landau-Ginzburg correspondence. So we try to understand that. The byproduct turns out to be can be used to calculate higher genus Gromov-Witten invariants. Okay, so I'll come back to this polynomial again. Control the time. Okay, so this polynomial in fact gives two things. One is quintic. Okay, so that's Calabi-Yau quintic, and then we have Gromov-Witten invariants. You can also consider this function as a function, and of course this function has a critical point. So there's a singularity, and therefore you have singularity theory. And in physics, it's called the Landau-Ginzburg model, and in mathematics, the corresponding invariants of the Gromov-Witten will be called FJRW invariants. Fan Huijun, Jarvis, and Ryan. W is for Witten. Okay, so in physical point of view, these two theories are the same. Okay, so therefore, physically, you can have identification of these two invariants, but you need to do some change of variables and maybe some transformations. And this type of thing is called the Calabi-Yau Landau-Ginzburg correspondence. And mathematically, genus zero case was proved by Scioto and Ran. Basically, just compute on both sides. I don't think we understand this better, but just compute, and then they found the correct transformation, correct change of variables, then they get the identifications. Okay, so now I want to move to the method. Okay, the method is first, we change our point of view. Okay, we have to change our point of view in order to move forward. So first, we consider C star action on C6. So C6 has coordinates. First 5 coordinates will be labeled by x1, x5. The last coordinate by p. And then the C star act on here with weights 1, 1, 1, minus 5. Which means t act on here by t1, t. This is the weight 1, 1. Here is weight minus 5, which means summation of the weights is 0. So it's a Calabi-Yau condition. Okay, so then you consider this GIT quotient. Consider this stack. Okay. And turns out that this stack under this C direction has 2 GIT quotient. One is you delete the unstable points according to one polarization, you get a KP4. Another is you choose another polarization. In fact, there's only 2 chambers, so there are only 2 polarizations. So choose another polarization, then you have another stability condition. So these are unstable points. You take those away, you modulus C star. Turns out that this is C5 modulo Z5. In fact, you can see these two are birational, which means if you collapse the zero locus, you will get this. So therefore, then you have 2 GIT quotient. Then you consider sigma model, which means a map from Riemann surface C to this stack. Okay, to this stack. Okay, so we have the. So now I want to talk about the first reinterpretation or reformulation of Gromov-Witten invariants by Huai-Liang and Jun Li using the method called p-fields. Okay, so instead of consider maps from curves to the quintic, so that's Gromov-Witten theory, now we consider maps from the curve to KP4. Okay, so this is KP4 here. KP4 here. Okay, so so this map can be described in this way. Okay, in this way, we have a curve C, a map to a quotient. So this is algebraic geometry, right? A map to a quotient is always correspond to line bundle together with the 6 sections. Okay. Which line bundle you are in depends on the weight, right? If it's 1, 1, 1, it will be line bundle L. If it's the t minus 5, it will be L to the minus 5. Okay. All right, so now I have a curve, line bundle correspond to the CC direction, and the phi I correspond to the first 5 section, that's coming from the C5, and the rho coming from the C minus 5. To another C, because the weight is minus 5, so I get a due minus 5. But suddenly I inserted this omega C here. Before, it should not have omega C, okay? But I insert omega C, I will mention this more often later, okay? And then you get a 5155 nowhere 0, so this condition coming from here, right? This cannot be 0 at the same time. Okay, so now I get nowhere 0. So this is the map. Okay, so people don't feel comfortable, but if you add the geometry, you know this is a map. Okay, just map information about the map. Okay, so you consider modular space of such things, modular space of such object. Clearly non-compact because you have sections in a vector space, right? So the section moves in a vector space. It's not compact. And also there's this extra row here. This extra row is called a P-field. The P-field is coming from this row. And this modular space, because it's non-compact, you cannot construct invariants at all. So you have to solve this non-compact issue. And yes, no, the co-section. This one? Yeah. This one? Sometimes they don't. Doesn't matter. It will live there as later on. In fact, this is due to the H1 by Serre duality. So basically, this row is the obstruction, which means you put obstruction in your modular property. Okay, so luckily, this modular space, in fact, has obstruction theory, whose obstruction sheaf has a map to O. So this is called a co-section. O to obstruction is called a section, but in this direction called a co-section. Okay, so this has a co-section. And once it has a co-section, Byung-Hong Kim and Jun Li developed a method to construct a compact subspace of the modular space. This is called co-section localization. And therefore, you will have a compact space, and this compact subspace, you can define invariants. Huai-Liang and Jun Li proved that the invariance defined in this way, in fact, is Gromov-Witten invariance up to a sign. So which means they gave a different or reformulation of Gromov-Witten invariance. Okay. So this is the P-field reformulation. Okay. So at this moment, you know, maybe we can ask, why do you do this? Does it help us to calculate? At this moment, we don't see it, but later on, we are going to see more the power of this reformulation. So now I will talk about FJRW invariance. So FJRW invariance was defined using analysis. Okay. So Huai-Liang, Jun Li, and myself, in fact, we give a P-field description, which is algebraic geometric description of this FJRW invariance. So let me mention that a little bit. So FJRW invariants of polynomials are defined by Fan, Jarvis, and Run using analysis. For the quintic polynomial, it is defined on a modular space of 5 spin curves with a section of a line bundle over the curve. And then you use so-called Witten's equation. But this Witten equation involves a d bar. I mean, the conjugate. So this is not the algebraic geometric setup. So before us, in fact, Polishuk and Ventrop already defined, at that time it's called the Witten's top chain class. Okay, they define that, use matrix factorization, and Scioto used K-theory to define also this invariance. At that time, they don't know whether these 3 invariants are the same. But at least these 2 are algebraic geometric definition. Okay. So now I want to give another interpretation of this definition. So what we do is we consider map to the orbifold. Okay. So remember the orbifold, in fact, is C6 minus this guy mod C star. So we saw this before in here. So one of the GIT quotient here. Okay. So the Gromov-Witten invariants go to this here by the Huai-Liang and Jun Li's work. So now FJRW goes to here, but I will look at this as a C star action. Okay, so the C star action, I rewrite this again in algebraic geometric setup, will come from a curve C. C star action gives me a line bundle. First 5 sections will be here, and the row will come from this. And then this condition says that rho is nowhere 0, right? Rho nowhere 0. Rho nowhere 0 means this line bundle is trivial, which means this line bundle in fact is 5 spin. So therefore, your modular space in fact is a 5 spin curve with a phi p field. So now the phi I will be a p field in this part. Okay. So we obtain modular space of 5 spin curve with the phi p fields phi I, and which is non-compact because of the p fields. P field move here. And again, this modular problem has obstruction sheaf, which emits a cosection, and then use this cosection to define a compact. You get a compact set in the modular space, and use that compact set to define the virtual cycle, and then we prove that that thing in fact equals this, equals that, equals that. Okay, in a narrow setup. So there's a broad and a narrow case. We consider a narrow case. Using the cosine localization, so we define this formulation. Okay, so then you may say, so what? Now let's come back again, and because this is a PPT, so I have to rewrite again. So Gromov-Witten invariants, Huai-Liang and Jun Li's work say that you can describe Gromov-Witten invariants in this way. And our work, P field description of FJRW given by this way. If you compare word by word, you can see that this line and this line are the same. The only difference are here. Right? What are the difference? The difference coming from the stability condition. Right? Because stabilities are different, so they are different. So now you can see, at least geometrically, they are the same almost. Right? Gromov-Witten and the FJRW are the same, except GID. Conditions are different. So, mathematically, Gromov-Witten invariance FJRW, in fact, is kind of phase transition. It's kind of word cross. Geometrically. So how do you do word crossing? So this is a master space by Matsuzuki and Sadis used long time ago. So in fact, this idea can be used here. So since you have two stability conditions, so there's a P1 connecting these two stability conditions. So therefore, that's the P1 connecting the stability conditions, and the Z is so-called master space. I introduce extra P1 parameter into the picture, and the C star will continue to also add on P1. So now the action on the first C6 is the same, and C star will only act on the U, on the first coordinate. And then you choose a triple line bundle with some action. Then you can find that these are the unstable points. You should delete these unstable points, and then you modulo C star. So that's the master space. Okay, so then you consider a map to the master space. And then again, because it's a C star, it corresponds to line bundle. P1, in fact, is also a C2 modulo C star. So there's a C star here as well. So that's N coming from here. And then the first 5 sections, row, similarly here. And then this has 2 variables. One is called mu, one is called nu. Okay, so then you can write this down. And these are these same conditions here. Okay, for example, for this one, that means this cannot be 0 at the same time. So 5155 mu, this is mu, cannot be 0 at the same time, nowhere 0. Similar for all these. And for this modular problem, you have numerical invariance, and then you need to introduce stability. So what's the stability? In fact, at that time, we defined this as Jun Li. What's the stability? He just finite automorphism, because at that time, finite automorphism seems to be natural condition introduced. So we use finite automorphism as stability. And then you get a modular space. Yeah. Yeah. Yeah, kind of. Yeah. I don't know. Yeah, but basically this is the parameter connecting these two stability conditions.
Yeah, like another singularity.
Oh yeah, there's another singularity somewhere in the middle. Yeah, yeah. Maybe later on I will write out. Maybe you can see that will maybe correspond to the other part, the thing that right now looks like missing. Okay, so this is non-compact because you have section involved. Again, the abstraction shift emits the co-section localization, and then you can get a virtual cycle, localized virtual cycle, but it is not automatically co-section localization give you a compact space. In fact, the key part of this work is to prove this guy is proper. In fact, it took many years, several years for me at least, to prove it's proper. Okay, so this is a crucial setup. Okay, once it's proper, and then you can do many things on this modular space. For example, we introduce extra C-star action. It's very simple. We just rescale the mu section, and then we do localization here, and we sometimes maybe it can work. Okay, so this MSP was developed by Huai-Liang, Jun Li, and myself and Melissa. So properness, in fact, this is the most important geometric features of this setup. Okay, so now I want to say that this MSP geometrically somehow give you unification of Gromov-Witten FJRW. So let me write down the map. In fact, this is the map. Okay. It's just this map. Okay. But we write map in this way. Okay, always line bundle with the sections. Okay.
Yeah. This properness, the kernel of the instruction the previous one, but now you added this P1.
Yeah, P1. Is it difficult to prove?
Yeah. Is it more difficult than the properness?
The P field, in that case, it's very simple because they can prove that the co-section localization is just modular space stable maps. For this one, why it's difficult? Because you have two weights. You link MSP, Gromov-Witten and FJRW, then you have weights positive, you have a weight negative. It's very difficult to prove that's proper. Yeah, naively, it's not proper usually. That's the difficulty. Yeah. Before you just have these weights, no negative weights. Yeah. Okay, so let's go here. So this is the map. Okay, so let me write down the map here, and with the stability conditions. In fact, stability conditions here are now very important. Okay, so let's look at. Now we have three cases. Answer your question. Okay, so this is a Gromov-Witten, this FJRW, this is something else. I don't know whether this would be something else you asked for. Okay. So one case is mu equals 0. If mu equals 0, because this is nowhere 0, so this is an honest map. Okay, 5155 will be the map. And then this nu is nowhere 0 because this is nowhere 0. Nu is 0. Mu is 0. Nu is 0. Nu is nowhere 0. That means this line bundle n is trivial. So line bundle information n disappears. Only L survives. L together with the 5155 will be a map to the KP4, and then that's just Huai-Liang and Jun Li's reformulation of Gromov invariants. And for this case, if rho is 0, if mu is 0, and then if mu is 0, then rho is nowhere 0 because of this condition here, and then the mu. Now, in this case, this is not 0. So this is a trivial bundle. So one information disappears. So you will get n is L2 and L5 tensor is omega c because mu is 0. So that's exactly a 5-spin curve with the 5 p fields. That's FJRW invariants by our work. Okay, so we see Gromov-Witten and FJRW in the same setup. And then this is something, this extra here. So this is rho equals 0, phi equals 0. Then you get this is nowhere 0. And then you will have this trivial. Then you get a modular space of curves. Probably that's something with something like. So mathematically, is if you do word crossing in a real case, you will get the Gromov-W, FJRW. And then there's a middle point. In fact, it's Artin singularity. You cannot cross the wall. Probably this is something you talk about. I don't know. There is something extra in the picture. But if I do P1, and then I overcross. And this overcross is not, I get nothing. The overcrossing gives me something extra here. This is, so in the calculation, this will be hot integral. Okay, so therefore, then using MSP, so Guo Shuai and Ross, postdoc of Yongbing Ren, so they computed genus 1 Gromov-FJRW invariants using MSP. And then as a consequence, they proved this Calabi-Yau Landau-Ginzburg correspondence for genus 1 case. And then at the time, we also try to see whether our method is effective. So we use torus localization coming from the MSP. And this Zhou is now Yang Zhou from Tsinghua University. And then we computed this, and basically we reprove or recover Zinger's method formula. Okay, so now you can see we don't do blobs. So geometry, we don't do nothing. We don't do anything in geometry part. But the combinatorics part is much more complicated. So Guo Shuai and Zhou Jie work a lot of stuff in order to overcome the. It's much beyond giving talks. Okay, the geometry is simpler, but the combinatorics is much more complicated. I mean, geometry is simpler than Zinger's work, but combinatorics is much more complicated than Zinger's work. So it's like a conservation law. Okay, maybe I don't talk about this. Maybe I will talk about this later if I have time. Why this is effective? Okay, but in fact, actual computation to higher genus come from genus observation by Guo Shuai when he computed. He found out that the formula he got is like a given tau stuff, but the given tau stuff is different from BCOV stuff. So how to see they are the same? He need vanishings. Some terms has to be vanished. So it turns out that he observed that if you change this one field mu to n field, n, and somehow suddenly many terms disappear, become 0. Yeah, it's very strange. Anyhow, I don't know why this is large n limit. Okay, whatever, in physics. But anyhow, if you change computationally, geometrically, I don't know why. But computationally, this is effective. Okay, so somehow just use this setup, many important conjectures can be solved. Okay, then over here you choose a bigger torus group, okay, to add. So for example, in NMSP, n for the large n, the computation of genus 1 will be just half-pay. And Guo Shuai, Jun Li, and myself, we set up this geometry part, which means we went through the MSP argument and tried to modify many stuff and prove that everything we need are okay. So proper, modular space proper, many stuff, localization formula, everything we got here. And then Guo Shuai, Huai-Liang, and Jun Li, they proved the Yamaguchi-Yau finite generation, and in this paper they proved BCOV. Okay, so it's very effective. All genus, yeah. Huh?
They didn't have.
They proved, yeah. I mean, this means they get. I was not involved, so they told me that they got this holonomic anomaly equation. Yeah, 40. Yeah. So all the conjectures are completely, fully solved without any condition. Okay, so now I want to move to general case. Okay, so the general case turns out that there are several issues when we generalize. Let me see, I want to go back maybe a little bit. It turns out that so over here we have to prove, we put a stability condition. In fact, stability condition is a crucial stability condition. Which one you choose is super important here. Okay, if you choose a different one, you make a wrong answer. Okay, so how to do that? In fact, the work involves the general GIT quotients. Okay. So first, in order to explain the things, I use my original example, MSP, okay, as a BB case. So the same Z, C6 times P1 minus some conditions I will not write it down, modulo the C star. Now I rewrite things. Okay, first I rewrite, instead of P1, I rewrite this P1 as C2 with extra C star action. Okay. So now I start with V1, which is a affine space, C5, C times C, this C6, and C2 coming from the P1, and then this extra C star action. So now I have two C star action. One original C star action go here, and the P1 goes to here. I get a group G. Okay. So we know that G acts on this space, this V1, by the following weights. There are two parameters, ST. S at here is 1, 1, 1, 1, 1, S minus 5, SU. And the T will act on UV only, so T here. And we introduce another C star action. So this C star action is called R chart. I don't know whether this is the right name. But this C star action, in fact, related to this omega coming into the picture. In fact, in general, it should be log. Okay. So let's remember, let's recall over here, this extra here. Why do we put this extra things here? Or how we explain it in a better way. So it turns out that you introduce extra C star action. Okay, C star for the R charge. And the weight is R, is the element here, just act on the P. Okay, now we have a bigger group, gamma. Gamma is G times this extra group. So this is 3 copies of C3 in this simple case. Okay, but in general, and then we also have a character. So this C star, in fact, coming from this character here, and the kernel of this character is this G. Okay, so this is a baby case of the final general setup, which means we have a bigger group of gamma, we have a character, then we have a group G, which is kernel of this character. Okay. So in general, we start with the reductive group gamma with the 2 characters. One is called epsilon. G is the kernel of epsilon. So in this BB case, this is just epsilon. Okay. And then you have this is the extra character, and this extra character gives you the stability. So this extra characteristic of G will be called theta. Theta will be a character of G. And then you take a V to be an affine variety. It's not that the V1 I talked about. The V is something else. This V has a gamma action. Of course, we have a G action. And then you take a GIT quotient with respect to this theta, and then you get X. So this X is the GIT quotient, which is our target space. Okay, so in general, we'll be a toric variety. So this is a GIT quotient of V by G with the stability defined by theta. So in our MSP set case, so gamma is this copy of C star. E is the natural projection to the third factor, and this extra theta, in fact, is given by ST squared. And the gamma, of course, acts on this V1 here, this copy. And then this extra condition here. This is usually in physics called potential, superpotential. And the P x1, x5 is a gamma invariant. You can check it's gamma invariant. And you consider critical locus of this function is over B. So critical locus of this function is over B. And you can write it out, and turns out that that's your critical locus. Okay. But in fact, this gives you the co-section when I mentioned earlier, co-section of the obstruction sheet coming from this. And the gamma acts on the V I write here, and then you consider theta semi-stable locus or stable locus, which is given by this, okay? And then you consider map C to the stack, okay, V1 mod gamma. Mod gamma. So this corresponds to principal gamma bundles. Okay, we knew that the map from a space to a stack correspond principal gamma bundles called P over C, and also with the gamma equivalent map to this vector space V1. And because in our baby case, the P is copy the group G, the gamma. Let me write down here is the simple group. Okay, so therefore this P in fact corresponds to 3 line bundles. Okay. Each give you one line bundle. So there are 3 line bundles here. And then you choose a character of gamma, for example, like the STR with the ABC. And then you can construct a line bundle on the trivial, in fact, it's a trivial line bundle on the V1, but with the group actions gamma through this character. Okay, so that means on the fiber, you just act on the fiber by the character. Okay, so for any map, Riemann surface to the stack, you can take a pullback. You can prove that this pullback is just this guy here. In particular, you pull back of this epsilon. Epsilon is a third factor projection, so it will be the L3. And then we write L1 to be L, Ln to be the n. In fact, this Ln will be the Ln we saw before in MSP. And then you consider the gamma equivariant map that will correspond to, remember, this corresponds to sections, this vector space, right? And then correspond to sections rho phi I for the L, rho for the L3, so this L3 here, and the mu for the L times n, This is just copy, okay, copy from here. It's not difficult. Okay, so now we define something called the Landau-Ginzburg quasi-maps for GIT quotient. So now you can see stable maps disappear. Before, when we talk about Gromov-Witten invariants, we use a stable map. And in fact, this observation by Zhou Yang, even when he was a graduate student, he observed that the stability condition we defined can be reformulated in a way that will appear later. Okay. So then, turns out that in a general setup, stable maps is not good notation. For example, at least I tried before, if I modify something, I cannot prove the modular space proper. It doesn't mean that modular space is not proper. It just means I cannot prove it. Okay, use my old method, I cannot prove the modular space proper if I make small change. And it turns out that Zhou Yang observed that probably the right definition should be quasi-map. Okay. So let me mention a little bit quasi-map. So what is this quasi-map? So in fact, it's just a map to this stack with a little bit extra condition. A genus G, K-pointed the pre-stable LG quasi-map. It's just a collection of a curve with markings and with a map. So usually when we talk about the quasi-map, we stop here. Okay. Now this extra here probably stands for the LG or stand for this omega term. This I mentioned many times. Omega term appears in our setup, sometimes unnaturally. Okay, but this stands for that. Okay, so this is a Riemann surface with a marking. It's a k-point at the genus G balanced twisted curve, nodal curve. So twisted means it's orbit curve, just orbit curve. Balance is this little bit extra condition. Okay, so now we consider the map to the to the stack. So in fact, it's a representable map because it's stack, such that this extra condition for people who knew quasi-map is just quasi-map condition, which means the unstable part should be discrete and also away from the special points. Special points means the markings and the nodes. Okay, so that's the definition of quasi-map, which means you allow yourself to go to some unstable points before you have to map to the semi-stable or stable part. But now I allow myself to go some unstable points, but only finite many. And also should be stay away from the special points, stay away from the markings, and stay away from the nodes. And then this extra thing here says that we require or we force it to have the pullback of this L, epsilon was in my picture before is character of gamma, should be isomorphic to omega log. So therefore, if I use this setup, then my rho is a section here. Okay, just by this setup. And then now my L3 is this is L3 by definition, is the omega log. So I replace this by omega log. The omega log comes naturally. Okay, omega comes into this picture naturally because of this extra stuff. Okay, so this is a little bit different from the ordinary quasi-maps because of this extra condition here. Okay, so how do you do? It's a little bit technical, but yeah, math talk need to go at least 5 minutes of technicality. Okay, so Landau is quasi-maps for GIT quotients. So how do we define stability? The stability is very important. This is basically found by Zhou Yang. Okay, so it's a little bit kind of complicated, but let me go through anyways because I have to go through to show that in fact it's not trivial matter. Okay, so what you do is we introduce this big omega consists of 3 things. First is S, then the A is very simple, just a number. Okay, it's just a number, and this is just character of a gamma. So this we saw already. Okay, so this character gamma. And what is this S? S is something new. Okay, so S is just a finite set of non-zero homogeneous elements in this equivariant sections. Okay, so the K can go from 0 to infinity, and the theta, this theta is this theta reached to the G. Okay, so you consider equivariant sections, G equivariant sections. Okay, so in our setup, we choose the A to be small in this range, and in our MSP setup, this S will be this homogeneous polynomials. X1 to the V squared, X5 to the V squared, U to the 10th to the P. Okay. And then for each F inside here, in fact, this can be further decomposed into direct sum of this type of stuff. Okay. So therefore, here's K theta, here's this extra C here, KC. Then for any F in here, we can define 3 terms. One's called the theta weights, R charge, or theta slope. Theta weight is just this K. R charge is just the C. Slope is just a ratio. Okay, very simple. So then for this A, we have to take A to be the maximum of all of this, bigger than this. But this is finite many because S is a finite set. So you can take a maximum. You take F to be bigger than this. And in our MSP setup, we can calculate the weights. Okay, for example, I write down the weights, and our weights are here, and the slopes are here. Okay, so what is the pre-stable LG quasi-map? Is stable, but we need to introduce, it depends on this big omega. big omega is a triple here, okay, triple here. And what is this so-called stable? Okay, so for people who knew stability quasi-maps, you saw that first you need to have this type of condition, and then you will have this. Okay, so for the quasi-map, but now it's LG quasi-map, which means for any non-special points, which means not the marking, not the node, you need to have a minimum of order of vanishing of this order here divided by the weight should be less equal to A. So usually for quasi-map, you just here. Okay, because we introduced this extra omega, so therefore you have to add slope. Okay. And then the next condition is Q line bundle here. This is known is positive. Okay. So now, the theorem proved by Huai-Liang, Guo Shuai, Jun Li, myself, and Zhou Yang is that if you take the V, okay, affine variety, the GIT quotient is projective. If this guy is projective, if S is full, so this is very simple technicality, so I will not talk about this. But anyhow, so if you assume that this GIT quotient is projective, then the modular space of stable LG quasi-map to X will be proper. So therefore, for example, I spent many years to prove proper. Now over here we be color of that. Okay, so Zhou Yang observed that this stability condition implies MSP stability condition, which means finite, automorphism finite. Okay, so this is not trivial matter because you have to search for some right modification. Okay, of course, the next step will be to do the computation part. Okay, so now we have everything ready, the geometry is ready, so then we have to do. Okay, let's start.
Any questions?
So can you, maybe this is an unfair question, but I'm trying to remind myself. So in comparison with Gromov-Witten invariants, we have the abstraction count. It's just a simple thing. Pull back the tangent onto what the average variety, look at the map, look at the difference. And then we have the key fields on them. This gets modified. The abstraction complex gets modified.
Yeah, gets modified.
I want to know when we have the modified space of the key fields on this master space, on this P1. Can you tell me, like, very simple version of what's the abstraction complex? I want to see how does it see the perturbation of this fluidity.
Yeah, I don't have in my mind. It's written down in the paper. Yeah. In all paper.
In your paper.
Yeah. In all paper. Yeah.
But essentially, the abstraction complex.
The second paper. Yeah, second paper. The first paper I just put proper. Second paper is about deformation theory.
So it is non-trivial, right?
Probably no, it's routine.
So this inducing P1, the extra P1, to the master.
Yeah.
Is it twisting this up?
Oh no, the introduction P1 does not
doesn't
change much. Yeah, no.
But then your stability parameter is on this P1. So your
stability
is on line 1 to the.
Yeah, that's right.
So, but the abstraction complex doesn't see.
Maybe see a little bit, not complicated. Yeah, because you have actual line bundle in here. Of course, that gives you abstraction. Yeah. So in fact, no. Sorry, it's very simple. It just let me write that here. L I. So the abstraction will be 1, and then it's just H0 of line bundles. Okay. In fact, the abstraction theory is very simple because you see we wrote everything in terms of sections. So this is your modular space. Abstraction will be H1, 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 H1. Very simple. Very simple. Yeah. This introduction of the P1 coming from this extra end here.
Other questions? Then let's thank the speaker again.
Thanks.